Today we're going to talk about molecular compounds, also known as covalent compounds. Now you'll recall when we talked about ionic compounds, we had this big network of ions. So there weren't any particular molecules. We couldn't say, oh, this here is a molecule, because that's exactly the same as this here, and they're sharing one of their pieces. So we've just got a big network of ions without any individual molecules. Now what we call covalent compounds or molecular compounds is when you find actual molecules. Now when we're dealing with ionic solids, we only use what's called an empirical formula. In other words, we just want to know the ratio of the number of one ion to the number of the other ion. And of course we're going to want that ratio in lowest terms. So we want to say things like, oh, there's going to be 3 sodium ions for every 2 oxygen ions. Statements like that. However, if we have covalent bonding or molecular bonding, then of course we're going to get molecules. And we're going to want to write a molecular formula. So these molecules here, they're called benzene. And the red circles here represent carbon, and the white circles here represent hydrogen. So we could give an empirical formula and say that there's a ratio of 1 carbon for every 1 hydrogen. But we'd rather describe the whole molecule and say that there's 6 hydrogens and 6 carbons in each molecule. So our molecular formula tells us how many of each type of atom in a molecule. So you might be asking yourselves, well, how can I predict if a compound is going to be ionic or molecular? Turns out it's very, very easy. It will be ionic if a metal joins with a nonmetal. And it's going to be molecular if you've got a nonmetal joining with another nonmetal. And you'll recall in your periodic table that looks a little bit like this, that everything over here to the left is a metal. And everything over here to the right is a nonmetal. And we'd usually consider hydrogen as well as a nonmetal. So it's very simple. If you've got something coming from the left-hand side of the periodic table, joining with something from the right-hand side of the periodic table, you're going to get an ionic compound. You're going to get an ionic network. However, if you've got 2 nonmetals joining, 2 things over on the right-hand side of the periodic table joining up together, then you're going to get a molecular compound. So let's see if we can use this idea of metal, nonmetal versus nonmetal, nonmetal to predict whether the following compounds are going to be ionic or molecular in nature. So pause the video, try this question, come back for the answer. First one starts with magnesium, way over on the left-hand side of the periodic table. So that is a metal. It's joining here with oxygen on the right-hand side of the periodic table, a nonmetal. So this is going to have to be ionic. Second one, carbon, over on the right-hand side of the periodic table, nonmetal. Oxygen, also a nonmetal. So this is going to be molecular. Carbon, nonmetal. Chlorine, nonmetal. So this one is molecular. And finally, we've got magnesium again over on the left-hand side of the periodic table. That's a metal. So this one's going to have to be ionic. Now the naming and the formulas for molecular compounds is going to be a little bit more complex. With the ionic compounds, we could always use the crossover rule to find out the ratio of one ion to the other. But when we've got 2 nonmetals, it's a little more complex. So for instance, let's suppose we take carbon and oxygen. they can mix together two ways. They can make carbon monoxide, but they can also make carbon dioxide. The only difference is in the number of oxygen molecules. So when we've got molecular formulas, there's more than one way that those atoms can join together. So when we're naming these molecular formulas, we're going to have to let people know how many of each type of atom there is. So let's see how we would name molecular compounds given a molecular formula. We've got a few rules. The first is that the element to the left on the periodic table usually stays on the left in the formula. So for instance, here we've got nitrogen and oxygen. We write the nitrogen first because nitrogen is to the left of oxygen on the periodic table. Now this rule doesn't always hold, but it's usually like that. The second element gets the IDE ending. So this is the same as with ionic compounds. And our first compound here is going to end in the word oxide. Thirdly, we're going to use prefixes to tell how many of each type of atom. And these are the prefixes that we use. And finally, for the first atom that we write, we don't have to use the prefix mono because mono is the default. So let's try this. This would be mononitrogen monoxide because there's really one of each, but we don't write the mono on the first one. So this one is simply nitrogen, but then we've got to say that there's one oxygen, monoxide. So the default prefix for the first term is mono, and we don't have to write the mono. But if we've got two of the first type of atom, then we've got to put in the di. Dinitrogen monoxide, because there's one oxygen. The third one here, we don't need to write the monocarbon, we just write carbon. There's 4 fluorines. 4 is tetra. And then we need the IDE ending on fluorine. So it's going to be carbon tetrafluoride. And finally here we've got 2 chlorines, dichlorine. Prefix for a 7 is going to be hepta. So we've got dichlorine heptaoxide. So let's try going in the other direction. Let's suppose we're given the full name. Can you write the formula? So pause the video, write the formulas for these 3, and then come back for the answer. So dihydrogen monoxide, that means there's 2 hydrogens and 1 oxygen. Nitrogen trihydride means that there's 1 nitrogen and 3 hydrogens. Carbon tetrahydride means there's 1 carbon and there's 4 hydrogen. And you might recognize the formula H2O. It goes by a much more common name. We call that water. And NH3, that's what we call ammonia. CH4 is what we call methane. So typically people don't go around saying these words. They use the more common names for the substances. The key physical difference between ionic bonding and covalent or molecular bonding is the difference between transferring electrons versus sharing electrons. So here in the ionic case, you'll recall that sodium has 1 electron in its outer shell, and that electron will transfer to the chlorine because the chlorine almost has a full outer shell. So the electron transfers across, and so we end up with a chlorine with a negative charge and a sodium ion with a positive charge, and then the positive and the negative attract in that network solid. In the molecular case though, it's very different. hydrogen has 1 electron in its outer shell, and oxygen has 6 electrons. So what happens is the hydrogen and the oxygen will share a pair of electrons, and they'll share a second pair of electrons. So now hydrogen's going to have 2 electrons in its outer shell. That's a full outer shell for hydrogen. And oxygen, because it's now sharing the 2 electrons from hydrogen, will also have 8 electrons in its outer shell. So once again, it gets a full outer shell. So ionic bonding is kind of like Emily and Sarah here. Emily's too hot with the blanket on, and Sarah is too cold. So Emily transfers the blanket over to Sarah, and now they're both happy. Sodium has an extra electron it doesn't really want. Chlorine needs another electron, so sodium gives its electron to chlorine. And covalent bonding is a little bit like this situation. Sarah and Emily are both too cold, so what they do is they share a blanket. And by sharing, they develop a bond between them. Similarly, hydrogen and oxygen both need more electrons to complete their outer shell, so they share some of their electrons, and that becomes a chemical bond between them. You can often recognize ionic compounds compared to covalent compounds based on their physical properties. For ionic compounds, think of table salt as a typical example. It's a crystalline solid. It's made of little crystals. And the attraction between the positive and negative ions in that network, it's very strong. And that means you're going to get very high melting and boiling points. And then because it is composed of iron, when it's melted, it becomes a very good conductor of electricity because the ions can flow. For the covalent compounds, we now can have gases and liquids, not just solids. And because the bonds aren't so strong, we have lower melting and boiling points. And then because we don't have the ions, the positive and negative charges to flow around, we get poor electrical conductivity. Now there are a number of elements that when you find them in nature, you don't find lone atoms. You always find the atoms joined together with a covalent bond. That is, you get a molecule of 2 hydrogens joined together, or 2 oxygens joined together, or 2 fluorines joined together. And these are going to be covalent bonds. And since the 2 atoms are identical to each other, the electrons are shared perfectly evenly. Ordinarily in a molecule, the electrons aren't shared quite equally. Kind of like if Sarah's a little bit bigger than Emily, she's likely to take a little more of the blanket than Sarah does. So what we'd like to do here is just find all of these elements on the periodic table. We've got hydrogens here, then we've got oxygen, we've got fluorine, we've got bromine, we've got iodine, nitrogen, and chlorine. So you notice this L shape here. And then of course oxygen. So whenever you write a chemical formula for these elements that are in the L shape, or for hydrogen, you're going to have to make it a diatomic molecule. So let's summarize the key differences between ionic compounds and covalent or molecular compounds. The first thing is, of course, for ionic, you get these network solids, as opposed to the covalent case, where, of course, you get molecules. So in the ionic case, you're going to get empirical formulas, which just tell you the ratios of the different types of atoms. Whereas in the covalent case, we're going to use molecular formulas that tell us the number of each type of atom in a molecule. In ionic substances, we talk about transferring electrons. Whereas in covalent substances, we talk about sharing electrons. In the ionic case, we talk about the crossover rule, so that we can figure out the ratio of the different types of atoms. Whereas in the covalent case, we use the prefixes to tell us how many of each type of atom will be in the molecule. And in the ionic case, of course, we get these crystalline solids with high melting points and high boiling points, because in general ionic bonding is very strong. In the covalent case, we can get gases, liquids, or solids where we're going to have low boiling points and low melting points because the bonding is weaker. And finally, we have the case of perfect sharing in diatomic molecules. And these occur in hydrogen and those elements that form the L shape in the periodic table, which includes most of the halogens, nitrogen, and oxygen. And that's all for today, folks. Thank you very much.